All right.
It's you.
It is me. All right.
Just do your own face.
Nobody yet. Pink cherry. I imagine. Well, some people said they were going to.
Now this is brown bag, but it's not at lunch, so are you talking like liquor? Oh.
Yeah. Or a brown jug. All right, we're going to get started, and other people can catch up. And if all else fails, it's being recorded to YouTube. Right. So, thank everyone for coming. Today I'm going to talk about Git and kind of the level beyond the initial stuff of Git. You probably all know how to do things like commit. You all know things about pushing to your repository. You know things about basic merging. You know things about adding things to your index, that sort of stuff. That's all very basic Git. Today we're going to kind of move beyond that. The first thing I'm going to talk about is some of the internal representations of Git and how it stores things on the file level, which doesn't necessarily always, it isn't always useful information, but it can help you inform you on some of the things that are happening inside of Git and help inform some of the decisions that you make when you're working with your repository. And then we're going to talk about rebasing, actually, which is probably the thing that most people are going to want to take away from this, and probably the thing most people are going to learn about. We'll get to that, and then we're also there's going to be a brief period where I preach about why you would rebase and some of the ways you should be rebasing. And after that, we're going to do a bit on workflows, Git workflows. Some of you are probably already familiar with Git Flow. I know there's at least one project you're using it. We're going to talk about some alternative workflows and some of the pros and cons between those. So, at its very basis level, Git deals with blobs. And a blob is nothing more than a set of bytes. What we've done here, Git being a new tool, you can actually get down into the bowels and see some of these really cool utility methods and utility functions that they've left in that it uses on the internal side, but you can just call them as a user. You never should unless you're willing to completely corrupt your repo, but you can do it. So what we've done here is we actually added a file to the staging area using git add, and then we just went ahead and said, hey, Git, tell me about this file. And it's telling us that it thinks that it's mode 10064, which is a fancy way of it saying this is an ASCII file, which it was. You can see that it has a hash, and actually in Git, everything has a hash, with a few small exceptions. But everything, by and large, anything that's real has a hash. And then you can see on the right, it's got the path to the actual file that we added. So the neat thing about blobs is that they're actually unique. If a Git has two files and it finds them both on the file system and they have the same bytes, the same blob, it would point to the same blob internally. It's part of how Git saves space. So if you add a file and then duplicate it, it only stores the file really once. On top of blobs are trees. And trees are really just representations of directories. That's pretty much it. We went ahead and we said, okay, well now we've got a file in the stage. We're telling Git, hey, write this tree. And so it created a tree. The tree has a hash like everything else. And then we say, hey, tree, tell me what's in you. And as you can see, the tree actually has a tree inside of it, because that tree is the root one. It's the root tree for that commit. So underneath it, it has the first folding, which is path. And then underneath that would be a tree for two, and then a tree for source, and then eventually would be a blob for the source, the actual source file. Commits are what contain trees. A commit, it's everything you're used to. It's atomic in Git, which means that it can't change. And it is, in this case, we took it and we actually took the tree that we had written and we referenced it with the hash, and then just committed it manually, which again you should never really do. But it's totally possible to do it. And we got back the hash of here's your new commit. And as you can see, we went ahead and just logged it and said, hey, tell me what about this commit. And it gave us back all the information you'd expect. I committed it, it had a message about it, and it has a hash. So commits in Git really are the atoms, and I don't just mean that because they're atomic. I think of them like atoms. They're the basis level that you really need to understand 99% of the time. If you understand how a commit works and functions, then everything else in Git is going to make sense, except for a few crazy scenarios where you'll need to know the quantum physics of Git and the blob tree set stuff. But by and large, you don't need to worry about it. I'm presenting it here just so you guys can actually see. Here's what is built up. The other thing about a commit is that it's actually, because it's just a snapshot of trees and files, it's a shot of your repository at a given point in time. It doesn't contain diffs most of the time. And it doesn't contain any extra metadata information. It just says, here's what I know about it. Until you start, when a repository gets big enough, some crazy things start happening, and then Git starts storing diffs for purposes of space, whatever. But the commit itself contains nothing but the snapshot of your tree. So the next question then is, well, where did diffs come from? So when you're thinking about Git, you think about it in terms of commit topologies. That's the easiest way to think about it. Normally, when you're thinking about a version control system, you're thinking about the files, and you're thinking about the diffs between those files. And in Git, the files are really almost taken care of for you. I mean, you still have to add them. You still have to care about them. They're what you're saving. But as far as managing what they actually look like in regards to each other, there's not as much work to do, because Git handles a lot of it for you. So what you should be thinking about instead is these commit topologies. Instead of thinking about necessarily something as a branch or thinking about something as a feature, you think about it in terms of the commit topologies instead. Instead of a branch, it is a line of commits that you're attempting to do something with. You're trying to put it somewhere else, or split it apart, or pull one piece out. So the files in the tree, the blobs in the tree, is really just fading into the background when you're thinking about Git on a day-to-day basis. So the question then, like I said, is where do those diffs come from? And the diffs actually come whenever you put two commits next to each other. Git will actually create those more or less on the fly. So here we've got two commits, commit 1 and commit 2, on the left-hand side and right-hand side. File 1 is, or commit rather, 1 has file 1 in the root. And then it has a directory, but know that, which has file 3 and file 4 in it. On the right-hand side, you've got commit 2, which has file 2 at the root, and then a directory underneath it with file 4 and file 5. File 1 and file 2 actually share the same bytes. They're the same file in the byte representation. So what's going to happen is Git is going to see that as a rename. And actually, if you change the trees that it lived under and kept it with the same bytes, it would see that as a move. And you guys have probably seen that before as you drag stuff around in your IDE or whatever. Git will automatically pick up that things are moves or renames for you. File B, or file 3 there, which corresponds to blob B, exists on the left-hand side commit, but it doesn't exist on the right-hand side commit. So Git is going to interpret that as a remove. It's going to show you all of those lines are missing. Similarly, file 5 down there on the bottom is not on the left-hand side, but it is on the right-hand side, which means that it's going to be interpreted as an add. And then file 4, which exists in both places in the same tree, is going to be interpreted as a diff between those two files. So you could put any two commits next to each other and get a diff of them. It may not be meaningful or useful, but you could do it, because those things get generated more or less on the fly. Again, once a Git repo gets big enough, it starts doing some stuff to save space, but it's still the concept still holds. You can still think about it this way, and everything makes sense. So now we're going to go into an example. So this is just a folder, and we're going to go into a Git repo that I've got. We've got some commits. And what we actually have here are Magic the Gathering decks, because I'm a huge nerd, and because I hate the recipe example that most people give when they talk about Git or version control. So if we look at this guy over here in a visualizer, you can see that it's a line of commits. Again, it's commit topology. What we have here is actually a DAG, a directed acyclic graph of commits that point to each other. It's not great for people in the back, but there are arrows that point downward. So you can see that this commit has a blue arrow pointing to its parent, and it has a red arrow coming from its child. Branches in Git are nothing more than pointers. And you can see that. We've got two of them here, MTG 2014 Standard and MTG 2014 Legacy. And these guys do nothing more than point to a specific commit, a specific hash that references a commit. That's it. And head is exactly the same thing. It's nothing more than a pointer. So if we go into head and we said, hey, what do I have left here to commit? It looks like I've been working on some block stuff. So this is some data, some decks that I've been adding for a backend for a RSS, or not RSS, RESTful, service that's going to be delivering Magic the Gathering decks for some visualization on the front end. And I'm adding a new format. So I've got two tags here that are Magic the Gathering formats, and it's just basically different ways to play. Don't worry about it. It's an arbitrary reason to make a branch, basically. So we want to add a new one. Let's add a new format here. And then we go ahead and add all of the files to it. You can see that when we added it, it picked up where we were actually just at. It said, OK, here's your head. You're branching at this particular location. Let me actually check that guy out. There's the wrong command. And we can commit this guy. And when Visualize picks up, you can see that we've got a new commit on top, down the new branch. Tags in Git are exactly the same thing. There are two kinds of tags. Actually, there's a lightweight tag and an annotated tag. Lightweight tags exist as nothing more than like a branch. They're just a pointer. Annotated tags actually are a pointer that has a metadata attached to it. So you can git tag -a and give it a name. And then give it a message. We're going to tag because the season's over. If I can actually type it. There you go. So again, you can see that we just got a tag. And it's, in terms of Git, it's really nothing more than a pointer to a specific commit. Right. So all of that's pretty basic. And most of you probably understood most of that already. So the piece of information that is interesting is once you have a tag or you have a name for a commit, and both a tag and a branch and a hash for a commit are all valid names. They all reference a specific place. Once you have one of those names, you can start manipulating it. You can use the caret operator, which you may or may not have used, and the caret operator simply moves us up one level. It says, hey, give me the parent of this name. And you can do that 3 times. You can do that any number of times, an arbitrary number of times. Of course, after a while, that starts to get hard to type, so you can actually use the tilde format instead. And head tilde1 is actually the same thing as head caret 1, or head caret, rather. And head tilde is an abbreviated way of just doing head tilde 1. All of those will actually do exactly the same thing. So if this is our head, then head tilde 1, or head tilde 1 is here, head caret is here, and head tilde is here as well. They're all the same thing. And then as you move up, it'll actually keep going. I mean, you can chain up as many times as you want. So again, head's just a name. And interestingly enough, once you have done a operation on a name, that itself is also a name. So you can chain those as many times as you want. You can do really crazy stuff to get into your repository wherever you feel like, if you need to. Of course, at some point, it becomes just easier to reference the hash of the specific commit you're looking for. But you can do it. It's technically a valid a name for a commit. The caret operator and the tilde operator form a a formal grammar, a DSL, that you can mess around with. So merging would be the other thing in Git. You guys have almost done merges, I'm sure. So I wanted to show what that actually looked like in the visualizer. And we can go to the 2014 standard branch. As it turns out, block is valid. Any deck that is valid in block is valid in standard. So we're just going to merge it back in. We're going to use the NoFF option. And NoFF actually does a specific thing for us. Git will try and help by default in merge. Git will try and help by saying, oh, you don't actually need a merge commit. I'm just going to advance the pointer for this branch to wherever you think it needs to be. If it can do it, if there's no conflicts, and if you don't have to resolve any specific changes. If you really do want the merge commit to exist, you have to tell it, no, actually make a merge like SVN would. And you can see there's a merge commit. The neatest thing about merge commits is they actually have two parents in Git, which makes sense when you think about it. They've got one, which is the native branch, the branch that they were applied to, and then one that is the branch that was the code, or where the code came from. So you can actually use the caret syntax to reference those as well. Head caret 1 references the first parent of a commit, and that would be the commit on the native branch, the one that was merged into. And then head caret 2 would be the foreign branch, the branch that you merged in. You can actually use that any number of times as well, because Git has this weird thing called octopus merges, which I'll probably cover at some point, where you can just merge n number of branches together, and Git will be like, yeah, that's great, and shove them all together into one commit. So you can actually have a commit with just an arbitrary number of parents. So head caret is really a shorthand for head caret 1. And then head tilde 1 is also a shorthand for head caret 1. They both go in the same direction. If you use either of those, they will move up the native branch. Head caret 2 is not head tilde 2. If you use those from here, head tilde 2 would be this commit, 2 parents up, and head tilde 2, or head caret 2 rather, would be this guy, the other parent. So that's something to not confuse. Git also, I mean, as you can imagine, this starts to be, or rather, this many commits, and if a repository exists for a large amount of time, it can start to get cluttered. So Git actually does have a garbage collection system, which I wanted to demonstrate as part of the internal stuff. So that looks exactly like what we saw, just another commit, or another repository rather. But in this one I say, I'm tired of legacy, it's a stupid format, it's way too expensive to get into. So I'm gonna get rid of that branch. The capital D we have to give it because otherwise it's going to complain about it not having, it's going to say, oh, you have a commit out here that's going to be lost. And so we have to basically give it a force option to say, no, we actually want that to go away. So the visualizer will show you, we've got a little gray commit floating out over there. That guy's not actually gone for a couple of different reasons. Git will keep it around for a period of time, which is one of the ways you can actually recover that sort of thing. And I'll show you how to do that probably in the third talk. Some of the mistake recovery stuff you can do with Git. So that guy's hanging out there. You can run into scenarios where you don't want them to hang out. For instance, if you accidentally commit a very large binary to your Git repository, which is not the smartest idea, if you do that, the repository takes forever to check out. It can take forever to do a couple different operations, as it's just trying to deal with the massive file you handed it. But deleting that commit and getting rid of it in your history won't necessarily get rid of it in the Git repository. So you can actually run a GC script, which is just this command. I just scripted it so I didn't have to type the damn thing. And all you're doing there is you're basically just manually calling the garbage collection in Git and say, here's a whole bunch of operators that I want you to tap on those, of options that I want you to do. So before we get into rebasing, I wanted to talk about why you guys should be rebasing. And so I'm preaching here, so feel free to take this with a grain of salt or completely disagree with all of my points. It's fine. If the best way to think about Git is commit topologies, if the sanest way to deal with it is following flows of commits and what commits move where and what commits are next to each other, then the argument is that the more cleanly you can make a commit, the saner you can make that commit topology. The smaller the commits are, the better flow from commit to commit, the more you're thinking about that actively, then the better off you're going to be, because it's going to be easier to understand. A very smart guy that I used to work with drilled this into my head, and I still firmly believe it. It's one concept, one commit. So that means if you're working on a feature branch and you come up against something that's a bug, and it's not related, even if it is related to your feature branch, that's a separate commit. You don't do the bug, fix the bug, and commit feature code at the same time. That one's pretty simple. If you're working at it and you say, hey, this guy over here has a feature that I could use. If I extend that slightly and add some functionality, I'll get to use that here to make my job easier. That should be a separate commit or a series of commits. If you're running across a place and you say, oh, wow, this unit test is terrible for this class I was going to use, and now I'm going to go fix it, that also should be a separate commit. There's an argument that says that those should actually be entirely separate branches in Git, because then you're cluttering up your peer review, basically, your pull request, with commits that don't have anything to do with the feature you were actually dealing with. But if you're focusing on the commit level, at least you're doing that. So commits then should be atomic, not just in the sense that Git has them as atomic, but atomic as in this is a change that I can make, and that can apply, I won't say anywhere, but as many places as I can think of. This change set should apply on this branch, and then back over here on this release branch that I have, and this hotfix branch. If I need to fix those 3 places, you want to make those commits as targeted as you can manage so they'll cleanly apply in as many places as you need to push them across your branching structure. And on top of that, commits don't exist in a vacuum. We saw that, we talked about the commit topologies. So commits exist next to each other, and so a feature branch or any flow of commits should be almost like a story. It should advance from commit to commit, and each one should be independent, but they should advance in lockstep, sort of some goal. So this is a quote from Linus Torvalds back in 2001, before Git was really a thing. And he's talking about a guy named Al, and talking about these patches that Al would submit, which were poetry in patches, as is the phrase that I really wanted to pull out of here. They are individually commits that make sense, and then they also make sense in the larger context of the feature. They're not just haphazard, I'm making this commit over here, and now I'm making this commit over here, and I'm making this commit over here. I'll be the first to say that my commits don't always measure up to that, but this is always the gold standard that I try to push myself to. So, and when you're working with those, I have a firm belief now that you get clean code if and only if you have clean history. Your code can be completely clean, by the book clean, self-documenting, and unit tested to the nines. And it doesn't matter if your history doesn't make sense. If you don't understand the context of your code and where it exists on a time scale in terms of where it's been and not just where it is right now, then there's plenty of room for misunderstandings between somebody else reverting something that you changed because they don't think it made sense, except that was what the customer wanted, or that was what the feature request, or that's what you had to do at this point to make this other stupid thing work in some completely different place. Again, the cleaner you can make those connections, the cleaner you can say, hey, everything here follows from each other, then the less likely it is that you're going to run into mistakes later. And again, we're not talking on, your code can be perfectly clean and perfectly well, work in that context, but knowing where it is in that time context is going to save you from even more mistakes. It's like the next level of moving upward. So when you're working on stuff, you should almost always err on the side of too many commits over too few. we're going to talk about rebasing, and that's really why you want to do that. It's way easier to combine commits in Git than it is to tear them apart after the fact. It's totally possible, but it's way easier to just go, oh, well, those two should be the same. So you kind of want to take the Chicago way approach with it. You commit early and commit often, as many times as you can think of. Like just, oh, I did this thing and then I committed it. No, I did this piece over here and now I committed it. Because after the fact, and we're going to go through this, you can change that. So I wanted to quote in here from, it's attributed to a guy who knows a lot about the winning battles. And I firmly believe that winning the battle for sanity in your commit history, and sanity in your repository, is winning the battle for sanity as a developer. And I mean that, like, literally, your sanity is at stake. The more crazy your commit repository gets, the more crazy your history gets, the harder it's going to be for you to figure out what the hell is even happening. And especially when there's a really crazy, stupid bug, and you're trying to find out who committed it, and it's, you know, it's actively on fire, the customer is calling every 15 minutes wondering where their fix is. That's when all of the hard work of maintaining a clean commit history, a clean repository, rather, is going to pay off. So, in the quote, Napoleon says, history is the history is the version of past events that people decided to agree on. And that's where Git really comes in. Because Git allows you to make history what you think it should be, what you think it should have been. You're no longer tied to, hey, well, Josh committed this thing, and then Matt committed this other thing over here, and then Jeremy committed this other thing. It doesn't matter. You get free reign, to an extent, over what you have in your history. And the way you do that is through rebasing. So what we're going to talk about is rebasing as cleanup, which is different from another type of rebase we'll talk about in a minute. So you guys can see the repository over here. And what we have is a line of commits. We've made a branch, and we've made a bunch of commits to it. There's a tournament happening at Krypton, and we've had someone on the ground with a tablet, a really crappy tablet, that's making commits a lot because he doesn't want to lose his work. And he's kind of harried because there's like 200 people there, so he's trying to keep track of everything that's happening. And he's made some commits that are, let's call it questionable. He's forgotten a couple things and then made separate commits to re-add those. He went completely drunk at the end and just made a really ridiculous commit message. And if you look at the actual files, he's committed the lunch orders from that day. So we get rid of this. We make this a clean history by rebasing it, by rebasing as cleanup. And we use a tool called interactive rebase to do it. So the first thing we need to do is figure out where that stupid bunch order got into. So what commit it's actually in. I have to type the actual command. We git blame, and we can see what commit came in. Came in this guy, at E164 DCA. So we type git-I, which turns on interactive rebase. Ooh, we have to check out the right branch first. No, we're on the right one, sorry. And we rebase onto the same branch we're already on. You can see we come off of the 2014 block, and we just say, put us right back there, but I want you to stop and show me what you're actually going to do. I never remember the way those things. There we go. There. So this is going to be a little weird the first time you do it. It popped open a text window at me. Why did it do that? What it's doing here is it's giving you the option to mutate history. It is providing you a list of commits in the order in which they'll be applied. So if you actually look at these numbers here, if you can see that, it's 001581, which is the first commit here, is the first commit here. So the order is actually flipped from how they live in the repository. It's giving you in the order that things will be applied. So you do have to keep track of that. But what it's doing here is it's saying, oh, what you can do is move these lines. You can copy paste these lines around, and it will actually change the order in which they happen. Because Git doesn't store diffs in the commits. You can just reorder them however the hell you like. And it will say, okay, well now the repository should look like that, and then it should look like that. So the other things you can do are reword, which is you can change a commit message, which is what we want to do here, because that's kind of dumb. And then we're going to go, oh, well, this is wrong number of lines for artspec, but artspec was committed up here. So we're going to put those next to each other. And then we're actually going to use a command here that is fixup. And what fixup does is it says, hey, I want you to keep all the changes that happened in this commit, but I just want you to fold it into the parent, and you can get rid of the commit message. So what will happen is those two individual snapshots will fold together into one with one commit message from the parent. You can use the squash command, which will keep the previous commit message as well. And actually, I'll cover an example of where you might do that. You have a couple other options. You can edit, which is what we want to do with this guy, E164, because that's where the lunch stuff came in. And that will actually let me change a commit. Git will apply the commit, stop, and then go, OK, you can do what you want. We'll show that example. The last thing you can really do is exec, which is a kind of cool thing. And exec will actually, you can add lines that are exec, and it will execute a batch function for you. So if you're doing an interactive rebase and you want to make sure that you can run your unit tests after each one, you can add an exec line after each line of this and make sure that the unit tests pass after each commit. So we have this the way we want it, and we save and quit, and Git says, OK, I'm getting to work. It rolls back history and then starts applying patches, making changes as we go. You can see that it changed the commit for mine. And you can see that now we're at this Andrew's deck, the commit for Andrew's deck. So now you can see that what we have here is an entirely different line of commits. Because a branch in Git, or any reference to a name, points to a hash, what that means is because a parent a commit's parent is included in its hash, it's hashed with it to create the hash for the commit. That means if its parent changes, the hash for the commit changes. It's technically a different commit. So the neat thing about branches is that they can actually, when they actually do define an entire DAG, an entire graph of commits, because if anything changes in it, they won't be pointing to the same commit anymore. It's kind of a cool way to save a bunch. They figured out a cool way to save a bunch of space with it. But it does mean that you get a bunch of this corrupt, which is why Git really needs that garbage collection functionality. Everything on the left-hand side, when we're done, is just going to be gone. We're not going to have a pointer to it anymore. So we're stopped at a commit. Git rebase will actually pause a bunch of different times. It'll pause if a commit doesn't apply cleanly. It'll pause every time an exec returns a return code of non-zero. So if like you're running a script and it returns a 1, an error code, it'll pause and say, OK, what do you want me to do about it? And at that point, you can actually, as you can see, you can continue. There's actually, you can abort. You can say to Git, nope, go back to where we were. And it will immediately return to the left-hand branch there and just say, nope, we're dropping everything on the right-hand side now. But in this case, we know that we have Andrew's deck in here. So what we want to do is go into this folder and git rm this lunch order. Actually, let me show you first. Intro 760. So this is what the commit looks like. It's got Andrew's deck in it, and then it has the lunch orders down at the bottom. You can see that it's a commingled commit, and we want to get rid of it. So we're going to remove the lunch order file. Great, it's added, it's removed, it's staged. So we're going to commit, or commit amend option rather. And you can do this even if you're not rebasing. You can actually say, oh, I left like 4 files out of that last commit. I really want those to be in there. Add them to your stage, and then use git commit amend, and it will automatically fold them into the last commit. So what it's telling us here now is, I'm going to change this commit. Do you want to change anything else about it? We have a chance to change the commit message if we want. And then it's actually going to show us down here what the diff is, or what the change is, what files will we change. And as you can see, the lunch orders one is now no longer there at all. And then we have to tell Git to continue. So now we want to change this commit message. And again, it's popping up the text editor to show us, hey, change what you want. You can actually edit your, if you're not a fan of Vim, you can edit your text editor to be whatever the heck you feel like. Emacs if you feel that way. I'm not sure Eclipse works. It might spawn an entire new Eclipse instance, actually, so that's probably not the greatest idea. But Sublime Text or anything else you guys have. So we'll give this the same commit, or commit message. And then move on. And in this case, you'll note that it didn't actually pause. It just said, OK, we're going to keep trucking afterward. So now we've got a new line of commits. Look at it, and oh, we forgot to do one. We didn't merge Chris's deck into Chris's deck. So we can just redo it. You can get Rebase as many times as you like until the commit history is as perfect as you want. I mean, obviously there's a point of diminishing returns, but you can actually just use single letters here as well if you're lazy, like me. And in this case, because Git didn't need to, it didn't stop and ask us for any information. It just went ahead and said, we're doing all this Rebase. And so you can see that our first couple commits actually stayed the same. The point at which we started changing, we diverged off into a new history. This history is different now. So now we've got a commit history we're proud of. And that's something we can actually merge back in. Wrong one. Oh, I was like that. Neat. Rebasing is also useful in another context. In this repository, we didn't have any extra commits in the block branch that we needed to worry about. Nobody else had been working there. That's hardly unlikely unless you're working in some far-flung feature branch that nobody else is touching. So realistically, it's going to look something more like this, where you have a line of commits, and then you have some other stuff. You branch back here, but somebody else has been working while you, in the meantime. They've merged another feature back in, or they've committed a bug fix or something. So Rebase will help with this too. We're on the NTG14 block, so we want, ooh, what are you doing? In the wrong way. We want to check out that 2014 Krypton open tag. You can see that this is actually the edited history that we went with. So what we do is we just rebase. We don't have to do interactive here. And we tell it, oh, go put me on top of 2014 block. Rebase me on top of this branch. Make my base this, is literally what the rebase command is doing. So all of that stack of commits are going to go live on top of this commit here. And it could be any number of commits you're sitting on top of. And Git will go ahead and pause in the middle of a rebase to say, oh, well, there's a conflict here. You have to take care of that before I can continue. So it never lets you actually plow through any conflicting commits. Every commit must be valid to go into the repository. If we execute this guy, you can see it starting just applying patches on top. And again, because history changed, we have a whole new line of commits. But the content of those commits is actually exactly the same as the other branch. So now we could merge those back in. if we wanted to, or do a fast forward rebase or a fast forward merge and merge block back with the crypt on open stuff, and then get rid of the crypt on open tag. So the important thing to note is you don't have to do those separately, and you probably shouldn't. You can interactive rebase onto something else at the same time and save yourself the trouble of having to do 2 different sets of edits. So, like I said, at least one project here I know of is using Git Flow. Is anybody else using Git Flow? Probably for cool? Okay. Git Flow is a merge-based methodology, which means that it's primarily focused with merges. And in fact, if you read the original article, the guy explicitly says that you should be using that no fast-forward merge so you get as few rebase-looking things as possible. There are other types of methodologies. There's rebase methodologies, and then there's some of them that are kind of combinations. It boils down essentially, in my opinion, to 4 of them. There's pure merge, which is more of a Git Flow thing. There's pure rebase. You can either keep that branch or you can delete the branch afterward. There's rebasing and then merging. And then there is rebasing with squash, and you can squash to a couple of different degrees. We have an example case here where we've got a develop line, and then we have 2 feature branches already existing, and then we're making a new one. We branched off of A and made a couple commits. We're doing stuff. B, feature branch B here, has some stuff that we want. It's got some stuff we have to extend off of, some things we need to expand on. So there is a commit here that's been merged in, is E. And we know that there's another featured branch out here, C, that is going to be merged in at some point in the future. Not right now, but it will be. So we're going to go through each of this example case, the exact same example case with each of these 4 different things. So in the pure merge strategy, the first thing you do is you want the code out of develop now. You want that stuff that was from feature branch B. So you have to merge that into your local feature branch. And you do that just with a git merge, and it will pull that code across and make a merge commit. While you're working on stuff, G, the commit G gets created, which merges feature branch C in. And then you commit your extension off of the stuff that B did in commit I. At this point, you've got changes in your develop, which means that you can't do a fast forward merge anymore. So to get your changes back, you make another merge, creating commit J. And at that point, what you've got is your feature branch, which includes one merge and possibly multiple merges, depending on how long it's been around and how many times you want to code. And then you have one merge back into your develop branch. This has a couple benefits to it. Actually, has a number of benefits to it. One is you don't lose context. That feature branch can always live, in your repository, as long as you don't feel it's cluttering up things, as long as you feel that context is useful. And you know exactly what happened in that feature branch, exactly what commits went into it. The downsides, rather, start to be that you can't, you have multiple lines of history at that point. There's a tool called Git Bisect, which is really cool, that will move through your repository history and try and find what commit introduced a bug. Using that with a strict merge methodology is actually really hard because it sees the entire merge as a single commit. And as a result of that, it can't bisect into it. You have to stop, go bisect into the branch, and continue. You can also get a ton of branches. You also get a ton of merge commits cluttering things up, depending on how often you're actually merging into your feature branches from develop or from other feature branches. And that can start to make things a little cluttered, and you can start to lose sight of a little bit of that clarity that you're looking for. So the complete opposite end of the scale is pure rebase. Same scenario, but the first thing you do, now that you need the stuff that was introduced in commit E, is you rebase, just like we did in that example. You say, okay, make my base E now, and you deal with any conflicts as necessary. So now somebody merges G in, and you go ahead and you say, oh, well, in a pure rebase strategy, it wouldn't be a merge. Those would both be rebases in. But for clarity's sake, I kept them as merges. So you go ahead and you make your commit now, your step extension off of feature branch B. And once you're done, you say, oh, well, now there's commits that I have to deal with back on develop. But instead of merging, you just rebase again. And so the important thing to notice, like we showed in the history, this has changed twice now. I got an underline and then a bold. I'd use prime notes like most examples do, but PowerPoint wouldn't let me. And commit I here has changed once. Every time you rebase, that's a new line of history. Just they're still the same snapshots. That hasn't changed, but they are different commits, so it's useful to keep that in mind. But once you have this, you've won, basically, because if you look, you've got a line of commits flowing from E all the way through I. So the only thing you need to do is move develop's branch pointer up. And then your commits fold into develop. So this is really nice because, first off, it's really great with Git bisect because every commit is available to you. You have a single line of history. Again, we don't here because I showed those as merge commits. But if they had been rebased in, you'd have one line of history for everything in develop. Downside is you completely lose the context of what those belong to. You can keep the feature tag around, but it doesn't tell you when it started, really. It just lets you know that this is where the feature branch ended. So you can keep a little bit of context, but you lose the perfect clarity of what's actually happening. So to mitigate that, you can kind of do a rebase with merge strategy. Again, we start with this exact same thing. And the first thing we do is rebase to get E. Once we're rebased, G occurs again, and then we make our commit, same as in the rebase, pure rebase. But once we hit this point, we rebase again, and at this point, we don't rebase back in. We merge into develop. And what this gets us is now we still have a single line of commits, really. It just moves over into a feature branch for a bit. So there's some clarity there that you gain, and you keep the context of still having a feature branch. The downside is it requires a lot more management about what you're actually doing and making sure that you're synced up with feature branches and that sort of thing.
Do you lose the bisect at that?
You do lose the bisect at that point too, same way. Anything with, as far as I'm aware, there's no way to go into a merge automatically in a bisect. If you complain loud enough, maybe they'll add it. So in order to kind of counteract that, you can do rebase with squash. Again, it's the same as the rebase pattern. Everything looks the same up to this point, except now, instead of merging or rebasing straight, you interactive rebase. And you say, all of those commits for that feature are now one feature. Now one commit, rather. And you can use the squash functionality so you keep those commit messages. So all of the tiny commit messages get folded up into one big commit message where the title of it is, this is my feature, blah. Once you have that, you rebase again. And then just like the rebase example, you just have to move that pointer up. So again, like the pure rebase strategy, you get that single line of commits, and Git bisect works in that case. The downside is that can be a really honking huge commit, depending on how you look at things. If it's an entire feature that you've worked on for a month, that's a massive commit to jump over, and a massive commit to even try to figure out what happened. It kind of defeats the single concept, one commit to a degree. I mean, it's still one concept because it's one feature, but you don't have any clarity anymore on what's actually happening. So you can break that out into a couple different ones if you want. Like here's major pieces of the feature instead. I'm not advocating for any of these in particular. I'm more just trying to present options as to what you can do, what Git and the power of rebasing will actually allow you to do. So if anything, I'm trying to start a dialogue to make sure people are at least making a conscious choice when they're working with their repository, instead of kind of a de facto choice, because that's what you picked at one point.
One thing we didn't talk about was which one of these might work better in an environment we have a lot of parallel work.
It's going to depend on how often you're branching from branches. And then on top of that, there is the distributed stuff is an entire complexity level on top of that. So once you start talking about pulling branches from other people's repositories and working with something like Bitbucket or Stash, there's an additional management layer that lives on top of that you have to worry about. And I didn't want to go there because I didn't want this to be a 2-hour talk. So I'm just trying to go for here's the basics of workflow, and you guys are smart. You can extrapolate to how the workflow would work in something like Stash, or how it would work if you start using Git daemon, and we stand up a local Git one and share things locally. Because yeah, there is a question of, well, do I push this to my repository, like Stash? Is Stash my golden repository? Does it mean that if I push something there, I can never change that history ever again? What's allowed to change history and not is a team-based decision. And it could be even a project-based decision, depending on what your needs are, how many people you have working on it, and how often how complex your code flow is going to be, or how complex your commit topology is going to be. So that's a long non-answer, I'm sorry. But so that's pretty much it for the stuff, or for my presentation, rather. If you were interested in the beginning stuff about Git and the blobs and trees, there's a really good, really short book, PDF, that's Git from the bottom up. It's free. And I'll send this out in an email afterwards. If you wanted to read the original Git Flow blog post, I'll give a link to that. Git workflow for agile teams is kind of that's the rebase with merge strategy. So he's written a paper on, not paper, but a short post on that. And then there was a good kind of compare and contrast that goes into a lot more depth than I did on merge versus rebase, and a lot more of the pros and cons from one of the Atlassian guys. And so that blog is up there, that link. The Git Pro book is actually really good. You can get to link from it from Git's site directly. It's also free. And it has, if you were interested in some of the times when I was hedging about when Git creates diffs and what it's doing when repositories get large, you could go read about Git pack files. Either there, or there's actually a really good description, or a really good question on Stack Overflow that deals with that. So that was quite a while. Does anyone have any questions? I'm going to move pretty fast. Nope. Okay. I hope you guys learned something. Hope that was at least enjoyable. Thank you guys for coming.
Good job with that.
Yes, thank you.